the speaker is Sara Lapan, and she will speak about attractive domains of certain maps tangent to the identity.
Thank you for inviting me to this conference. It's on attracting domains of certain maps tangent to the identity. So first of all, we want to assume that F is a holomorphic germ self-map of Cm that fixes the origin. So we can write F in this form. F of z equals P1 of z plus Pk of z plus Pk plus 1 of z, where each of these P sub j are homogeneous polynomials of degree j, and we're assuming that the kth one is non-zero. So if we then assume that P1 is the identity, then we call this map tangent to the identity, and k is the order of F. And then for notation, we have f to the n just denotes the nth iterate of f, and z sub n is the nth iterate of a point z. Okay, so I think everybody in this room knows the one-dimensional case, but so in dimension 1, we know from the Fatou flower theorem that maps tangent to the identity of order k have k minus 1 petals of attraction centered along particular directions. And so this picture shows the 3 attracting petals of the map z plus z to the 4th. This is from Complex Dynamics by Carlson and Ganlin. So for studying higher dimensions, we can generalize this in different ways. For instance, we could try to generalize the result by looking for invariant complex curves, or we could look for domains of attraction. So in this talk, we're going to do the latter, so look for domains. And then the rest of this talk, we're going to restrict to dimension 2. Okay, so some definitions, and these hold in higher dimensions, but I just simplified it to dimension 2. So if you have v in C2 minus the origin, such that pk of v equals lambda v for some lambda in C, then v is called a characteristic direction. And if lambda is non-zero, this is non-degenerate, and if lambda equals 0, it's degenerate. So some motivation for this definition, if we forgot the higher order terms and we just had the identity in the kth degree term, then points on the vector v would just be fixed, or if you look at just p1, then that point is fixed. The characteristic direction is fixed. So f has either k plus 1, not necessarily distinct, or infinitely many characteristic directions. Okay, and then we say that an orbit converges, so looking at z1, z2, z so on, converges to the origin tangentially to a direction if it converges both to the origin and when you look at the iterates, it's converging along that direction v. So Hakim, a proposition by Hakim, if f has an orbit converging to the origin tangentially to a direction, then that direction is a characteristic direction. Okay, so this condition star, I'm going to write on the board because I'm going to refer to it several times. So this is just assumptions that we're going to be making for the rest of the talk. So we have f is a holomorphic germ tangent to the identity. And of order k. So that means that we can write f of z as, or f of zw as the identity, plus pk of zw, and then we have higher order terms. And then we're going to assume that v is a non-degenerate characteristic direction. Okay, so a theorem by Call and Hakim is assume f satisfies this condition, then there are at least k minus 1 invariant parabolic curves for f tangent to v. So this is like one of the directions that could go in generalizing the low Fatou-Flower theorem. So last time I'm going to talk about that part. So then we have a definition here. So if f satisfies this condition, then the eigenvalue of the linear operator here, a of v equals dpk of v minus the identity, this is called the director of v. Okay, so Hakim's theorem. So we're going to suppose that f satisfies this condition. So holomorphic germ tangent to identity of order k with a non-degenerate characteristic direction. And we're assuming that the director, the real part, is positive. Then f satisfies the local property. So I'm just going to refer to this as local property. It's not standard. So the first condition, that one, there exists a domain omega invariant under f whose points are attracted to the origin along an orbit tangent to v. And then the second thing is the restriction of f to omega is conjugate to translation. So in the first coordinate we have translation, and the second one identity. Furthermore, if we assume that f is an automorphism of C2, then f satisfies this global property. So there exists an omega as in the local property, but it's also biholomorphic to C2. Okay, and then a theorem by Arizi and Rezi.
May I say something? It's not really by us. It's just by Kim. You can
Oh,
just
okay.
phrase it.
Sorry.
No.
It was in
Just
your
to be-
paper.
You
Okay,
can
so
find it in our article, but
by Hakim, but in their paper.
Yeah. Sorry.
So let f satisfy this condition. So if there exists a domain where all the orbits converge to the origin along v, then the director has non-negative real part. So what we have left is what happens when the director has real part equal to 0. Okay, so the three previous results also hold in higher dimensions. So now moving on to the work that I've done. So suppose f is as in this condition here, but there's only one distinct characteristic direction. So it turns out that in this case the director of the map is going to be 0. So the previous results then don't apply to this situation. However, we can prove something, well, we can prove the same result. Okay, so again, we're supposing f is as in here, so holomorphic germ tangent to the identity of order k and non-degenerate characteristic direction. But now we're assuming that there's only one direction. So then the local property holds. And furthermore, if f is as above is an automorphism, then the global property also holds. So a reminder what I called the local and global properties. So we have an invariant domain, and on that domain, f is conjugate to translation. And the global property extends to a biholomorphism of C2. Okay, so around the same time that I was working on this, Liz Vivas proved the same result for Fuchsian characteristic directions. And it turns out that if f satisfies the condition star and has only one characteristic direction, then that direction is Fuchsian. And I'm not going to go into the definition of Fuchsian, but unless you ask. Okay, so now the rest of this time we're going to spend going through the sketch of the proof of that theorem. So the first step, we're going to simplify f using a linear change of coordinates. The second step is the long step. We're going to go through 3 coordinate changes, and each time we're going to refine our domain and rename it omega, just to simplify notation. And then after we've completed those first two steps, then we're going to move on to the global result. Okay, so given f as in star, with exactly one characteristic direction, it can be shown that f is linearly conjugate to the following map with non-degenerate characteristic direction at 0, 1. Okay, so we have z is going to z times 1 plus zw times r of zw minus w to the k minus 1 plus p of zw. And then the w term is similar but has that extra z to the k term in there. And so here r is homogeneous of degree k minus 3, and p and q are of minimal degree, at least k plus 1. So, oh yeah, okay. So this term right here, that's the identity plus pk term, and for w, that is the identity plus pk, so the other are just the higher order terms. Okay, so for this talk, I'm just going to assume that f is as above, and that k equals 2, and that means that r is going to be 0. And we're also going to assume that p and q equal 0. So we have this nice simplified version of the map that we're going to work with, but this all works without making that assumption. So I'll go ahead and write that down. I'll write on the other side. Okay, so we have f of zw equals z times 1 minus w, and w times 1 minus w plus z squared. Okay, so we finished the step 1. Now we're on to step 2, and we're going to start with our first coordinate change. So let psi 1 be the map zw goes to w over z squared, comma 1 over w. And we're going to call our new coordinates u comma v. And then the inverse of this map looks like this. And it's not defined everywhere, but we're going to restrict the domain so it's defined. And psi 1 is sending the point 0, 0 to infinity, since the characteristic direction was 0, 1. So w over z is going to infinity, and 1 over w goes to infinity. Okay, so we're going to fix some r, some large r, and then a small delta between 0 and 1, and theta between 0 and pi over 4. And so this is the first domain we're going to work with, and it looks kind of messy, so I'll just draw a picture of it. So if we fix v first, then the domain looks like this. So this is real u, and we have in imaginary part of u there. So we have a bound of theta here, and then r, and then it's bounded above by the v term. So u is less than delta v to the 2/3. So that's what it looks like in the u coordinates, and then if we fix u, then we have a smaller angle here, so it's theta over 2. And then now it's bounded below by this part, so v is greater than 1 over delta times u to the 3/2, and it's not bounded above. Yeah?
Morally, is the idea that since you're going to 0, 1 direction, the z squared term is not so important, and the rest of the map clearly is like w times 1 minus w. If w goes to 0, then z goes to 0 as well, so z doesn't matter then? Or is that not morally, let's say?
Yeah, I guess you could say that.
Yeah.
And, this is, yeah.
Yeah.
Okay, so that's what our omega looks like, and when we do coordinate changes, it's going to keep, for the most part, looking like that, and I'm not going to write out what this looks like because it gets kind of messy. Okay, so on this domain omega, psi1 maps, so psi1 inverse of omega to omega, this is a biholomorphism. Okay, so we're going to denote f after a coordinate change, still by f, and recall this notation, so the f of uv equals u1 comma v1. So now we want to see where what happens to u and v after we apply f. So just by definition, we have that u1 equals w1 over z1 squared from the coordinate change, and then after a little computation, we get that u1 equals u plus 2 over v plus terms of order 1 over v squared. And then for v1, we have from the coordinate change it equals 1 over w1. And then we do some calculations, and we get that it's going to be v plus 1 plus terms of order 1 over u and 1 over v. So we have some small terms there. And we use these expressions for u1 and v1 to show that omega is invariant under f. So it's just a matter of checking all of the conditions that omega satisfies. And so very roughly we have that on omega, Vn is going to behave like v plus 1 plus n, because these O terms are small, and that un is going to behave then like u plus 2 log n, because we have this like 2 over Vn is like 1 over, or 2 over n. But these O terms are large enough that we're not done yet. So it doesn't quite behave like that yet. Okay, so now we're moving on to the second coordinate change. So we want the second coordinate to be a Fatou coordinate, so it's just translation, tau when we apply f. So tau of f equals tau plus 1. So the naive approach would be to just define tau to be this limit as n goes to infinity of Vn minus n. And then we would have that tau of f equals tau plus 1. But the problem is that these terms aren't going to converge because we had the 1 over u and 1 over v terms, and those aren't going to converge. And so we have to change the expression a little bit more first. Okay, so let phi naught and phi 1 be holomorphic in the u component of omega, so they only depend on u. And we're going to define them later. So now we're calling t of uv equal to v times 1 plus phi naught of u plus phi 1 of u over v. So these terms we're using to get rid of our O1 over u and O1 over v terms. Okay, so after we do a computation, we get the expression for t1 is going to be t plus 1 plus some differential operator in u involving just the phi naught term, and then plus 1 over v times a differential operator in u involving both phi 1 and phi naught, and then terms of O1 over v squared. So those O terms are small enough that we can now ignore them. So we can find phi naught, so if we find phi naught first and then find phi 1, so that we can get that this term and this term both equal 0. And so then our expression for t1 simplifies to just t plus 1 plus O1 over v squared. So the v term, vn, we had before it behaved roughly like n, but not perfectly, but since it's close enough now, these terms are going to be very small. So we can use now what was before our naive approach, and let tau be equal to the limit as n goes to infinity of Tn minus n. Okay, so now we're ready to complete our second coordinate change. So we're going to leave u as is, but I guess substitute tau in for v. And so we get now that u1 equals u plus 2 over tau plus 2 phi naught of u over tau. And then terms of order u to the 3/2 over tau squared. And tau 1 equals tau plus 1. So these terms are sufficiently small because the tau behaves roughly like n, and the u terms behave like kind of proportional to log n. So the O term is small there. Okay, so there is a domain that can be defined in a similar way that we had omega defined over there, and on which psi2 inverse is a biholomorphism onto its image. So we're just going to rename that omega and keep going, but it looks the same, just some of the constants are changed. Okay, so down to coordinate changes, we're on to our last one. So we want the first coordinate to just be the identity. And so again, we have this naive approach saying that sigma equals the limit as n goes to infinity of un. And if we had that, then it would be the identity sigma of f would equal sigma. But this fails because the limit does not converge. So we have to do another, so we have to work with that coordinate. So let alpha of u be holomorphic in the u component of omega, and we'll choose it appropriately. And define s of u tau to equal u minus 2 log tau plus alpha of u. So let's go back to u. So in u1 we had this 2 over tau and the 2 phi naught of u over tau terms. Okay, so the term 2 over tau can be removed by this negative 2 log tau term that we have right here, and just adding small o terms. And the 2 phi naught of u over tau can be removed by this alpha of u term, and just adding small o terms. So yes, I'll write up what the alpha of u term is, in case you're curious. So alpha of u, so you fix some u naught in the domain, and alpha of u is just negative the integral from that point u naught to u of phi naught of zeta times 1 minus phi naught of zeta d zeta. Okay, so assuming that we do get those terms to cancel out, now our S1 term is equal to S plus O of 1 over u to the 3/2 tau. And now we can do this approach to say sigma equals the limit as n goes to infinity of Sn. So we're ready to finish our third coordinate change. So we have psi3 maps u comma tau to sigma comma tau, and now f acts on our new coordinates just like translation. So sigma tau goes to sigma comma tau plus 1. And we can find a domain on which psi3 is a biholomorphism, and that is invariant under f. So it's similar to this, but we have to add in something to account for the 2 log tau term that we have here, because that affects s. But it looks similar in definition to that. Okay, so this is concluding the first step of the proof, which is the big part of it. So we have, if we let capital psi be all of the coordinate changes, then what we have here, we have zw and omega Well, we have that this sorry, I forgot what word for it. Anyway, it commutes, yeah. Yeah, the diagram commutes. And so F acting on ZW is just acts like translation in our new coordinates. And so therefore we have that the local property is satisfied. Okay, so then the last part is showing the global result. So now we assume that F is an automorphism, and this is just a note that we can find an automorphism that is close to F using this theorem by Weikart and Buzzard and Forstenaerick. I think they were separately. So let P equal P1, comma, dot, 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 Pn for n at least 2. Let this be a holomorphic polynomial self-map of Cn with P prime of 0 invertible, and let D be greater than or equal to the max degree of all of those PI's. Then we can find an automorphism that is very close to the holomorphic polynomial that we started with. So we can use this to find an automorphism that is very close to this, to that map. But we're going to assume that there is such an automorphism. Okay, so using some standard techniques that Liz Vivas and Weikart and some other people also used, we can extend the local result. So we let capital pi be the inverse image of all of these omegas under F. And we extend the domain of the coordinates tau and sigma to this capital pi. And we do it as follows. So sigma of psi2, psi1 of ZW. So this is the same thing as just the first component of capital psi. We define that to be the same, like act the same way on the antiderivative of the point ZW. And then for the second coordinate, so tau of psi1 of ZW, which is the same thing as the second component of this capital psi, then that acts, so tau of psi1 of Zn comma Wn minus n. So this accounts for this coordinate being the translation coordinate. Okay, so Zm and Wm are in omega for some m, but Z and W don't have to be in omega. So these are well defined and they extend to psi, and so putting all of that together, so these two together, we have how psi acts on a point, how we can define it. Okay, so it takes some work to show this, but they're using standard techniques, like I mentioned other people who did this, to show that psi of capital pi is equal to all of C2. And so then we have a biholomorphism from pi to C2. And so this just means that pi is going to be a Fatou-Bieberbach domain. And it follows that psi of f equals psi plus 0, 1, so it's just translation. Therefore, we have the global property is satisfied.
Are there questions?
So, what if condition star is not satisfied?
So which,
You had
yeah, so,
you had the other condition star, right?
no, this was the condition star.
Okay, but I couldn't write it down. But you had some other assumption under which your result.
Oh, yeah. So the other assumption was that there was only one characteristic direction.
Yes.
So there could be k plus 1 or infinitely many, but There's just one distinct one.
So what if there are, what in general?
If there are more than it depends on what the director is. So I didn't make any assumptions on what the director was. So if we know that the real part of the director is strictly positive, then we have the result holds. And we know that if the real part of the director is negative, then it fails from this, I guess, also by Hakim.
Yes.
So when it's equal to 0, we don't, like, it's not all figured out yet.
What happens are the perturbations of the iterator? Simple about that. Are the perturbations of your parabolic map? So what happens with these petals? Are they completely destroyed, or there are some memories of them?
I don't know how perturbation, like, how that would affect. The only way I could answer that is how that would affect the director, and I haven't get it. So if the perturbations affected what the director was, if it was the real part of the director, then we know something about it, but I don't know anything else.
So for instance, you have presumably this Fatou-Bieberbach domain for attracting petal, and maybe for repelling petal you have another Fatou-Bieberbach domain, so you have some transit map, you see, so all this is a wrong picture.
There are a lot of possible perturbations.
You can imagine.
Question?
So suppose you have a convergent orbit of this point, and the question is that orbit always tangent to some characteristic direction?
Sorry, I couldn't hear you.
Suppose you have a convergent.
No. The answer is no.
The answer is no.
What happens when the real part of the directory is 0?
Sorry?
When the real part of the directory is 0, then it can happen that you have an orbit going to the origin just.
Just go on. If you blow up.
You wrap it doesn't convert to the direction.
There's a question?
No, thanks again.
Sara?